Bismillahirrahmanirrahim. This is advanced linear system theory. We're having question homework number 5. Question number 1 statement says that we are having a transfer function in which we have to represent this transfer function in the Jordan canonical state model form. Question number 2 says that we are having a P positive definite matrix. So we have to show that this matrix P is positive definite by definition. Similarly, we are having for a positive definite P matrix, Q transpose PQ is positive definite for any invertible Q. Question number 3 says that show that the following system is internally stable using the P matrix, which is the solution to the Lyapunov equation. This is the system state space representation, the state model. Check the B stability when the first element of X is measured. So this is the solution of the question number 1, which the transfer function is given over here, and by just arranging, we are having this small arrangement here. So this is the Jordan canonical representation of this transfer function. Here, this is the block number first, and this is the block number 2. We are having a poles of multiplicity 2 here, 2 poles at the same position, and we are having this is the third block in which we are having the poles of multiplicity that is equal to 3. So this is the block number 1. This is the block number 2 for the 2 poles of multiplicity, and we are having the block number 3 in which we are having 3 poles of multiplicity. So here we are just this is the input and this is the output of this system. So we are having these are the loops. Similarly, here we are having 2 loops in this this block, and we are having 3 in this block. We are having 3 loops. By assigning the state to variables, this is equal to x1. Here, this is the x1 dot, and here is the one integrator. For 2 poles of multiplicity, we are having 2 integrators, one over s here and one over s here. Similarly, for 3 poles of multiplicity, 1 over s is here, 1 over s, and 1 over s here. So these are the state variables. This is equal to x1. So x1 dot is basically equal to minus x1 plus u of s. Here, this is the input. This is edit here, and this is the input. This integrator. Similarly, this is x2 in this part, in this loop, and here before the integrator we're having x2 dot, and x2 dot is equal to minus 3 times x2 plus x3. So this is written over here, and similarly x3 is equal to x3 dot is equal to minus 3 times x3 plus u of s. Similarly, we are having x4 term that is equal to x4 dot is equal to x5 minus 2 times x4. Similarly, x5 is equal to x5 dot is equal to minus 2 times x5 plus x6, and x6 dot here is equal to minus 2 times x6 and u of s. So this is represented over here. X1 dot that is equal to minus x1 plus u of s, and similarly x2, x3, x4, and xs up to xs are represented over here. So in standard space, we can represent it. This is the state matrix form. This is the state vector x dot, and we are having the system matrix A. So this is here we are having one Jordan block, and this is the sub block here, and this is we are having minus 3 minus, this is the Jordan sub block 2, and we are having a sub block for minus 2 and minus 2. So this is the third block, third sub block Jordan block, and this is the system matrix A, and this is the system matrix B. Similarly, these are the 3, 2, 5 are the output here. This is the 3, this is the 2, and this is the 5. So these are the output of the these are the values, output values. Question number 2 says that we are having a matrix and we have to show that this is a positive definite matrix. Well, there are the other methods to calculate this is whether this matrix is positive definite or not, but here we will use the eigenvalue method, which says that we are having a if you are having a system matrix E, symmetric matrix P is positive definite if all eigenvalues are strictly positive. That is, lambda I is greater than 0. So determinant of lambda I minus P is equal to 0. We are calculating the lambda I. So these are the this is the calculation lambda minus 1, lambda minus 1 here, the same values here appearing in the diagonal, and this is minus 1 over 4. So that is the simple a plus b into a minus b form in which lambda 1 comes out to be 1 over 2, which is greater than 0, positive value, and lambda 2 comes out to be 3 divided by 2, which is greater than 0 and is also positive definite value. So as all a eigenvalues are positive, therefore the matrix P is positive definite. Similarly, if you're having a matrix, and we can also show that by the principal minor here, this is the one which is greater than 0. So this and similarly the determinant of this matrix is also greater than 0. So we can also show that this is a positive definite matrix. In question number 3, we are having the positive definite matrix P show that Q transpose PQ is positive definite for any invertible Q. Well, generally for any positive P matrix that is in the quadratic form, we are having a scalar function v of x that is equal to the x transpose t p x for all such that x is not equal to 0. So if we are having this value, this should be greater than 0. This scalar function should be greater than 0. So for a full ring invertible Q, we need to prove that Q transport T P Q is positive definite. That is Y T Q T P Q is greater than 0. And here, just by a little bit manipulation, that's Y T Q T, and that is equal to P Q Y for all Y that is not equal to 0. That is Y is strictly positive value. So yt and qt that is equal to qy. This is the matrix identity yt qt that is equal to qy. So we can suppose that this x is equal to qy, and so that it will becomes in this xt into px form. So here in this case, this x is strictly positive, and here in also we are having this y, and this y is also strictly positive. So which shows that this y by definition, which is a positive definite, and hence it is proof that for any we are having a positive p definite matrix. If this we have proved that this q transport p is positive definite matrix for any invertible q. Similarly, we are having question number 4. The question number 4 says that we are having this state matrix with the state space representation of this system. This is the state vector x dot. So this is the matrix A, system matrix A, and this is the system B. Also, here we have to find the internal stability of the system, the one of equation. Similarly, we have to also check the B stability, whether the system is a bounded input or a bounded output. There should be a bounded output. So in the first phase, we just assume that this is a positive definite symmetric matrix P, which is equal to P11, P12, and similarly P22. From Lyapunov equation, ATP, that is A transpose P should be plus PA should be equal to minus Q. So for any positive definite PD, here is a unique solution for P, that the Q should be any matrix, but the P should be, the solution of P should be unique. Let the value, so we are here, we are supposing the V of the value of the Q that is equal to identity. So that is equal to, by putting the values of the A and P and similarly PA, and that is equal to minus identity matrix. So by just manipulation, by calculating, multiplying these A transport T with P plus adding, and then we are having the coefficients which are minus 2P11 and here. So by just comparing the coefficients, so P11 comes out to be P1, P1, P22 is 1 over 3, and similarly we are having P11 that is equal to 1 over 2, and P12 is equal to 1 over 6. So this is the P matrix. This is the which we have. This is the P is a matrix, and in which we have calculated this. Now we have to show that this is a positive definite matrix. So that again by lambda I minus P, we have calculated the values by using the quadratic formula. Lambda 1 and lambda 2 comes out to be positive values, which shows that the P is a positive definite matrix. From the system matrix A, we can also see this is the system matrix A, in which is in the upper triangular form. So here the eigenvalues, lambda 1 is equal to minus 1 and lambda 2 is minus 2. These are strictly negative values. And for the system stability, for the asymptotic stability, the lambda, these values, the eigenvalues, should be less than equal to 0. So these are less than equal to 0. This is the condition. So this shows that all the poles of the systems are strictly negative. That is, as the system matrix A eigenvalues are real values, so all the real values of the eigenvalues are less than equal to 0. So therefore, the system is internally stable. To check the BU stability, when the output is taken across the x1, so this is x1, C comes out to be 1, 0. Similarly, this is the transfer function g of s, which is equal to y of s divided by u of s, and that is C Si minus A inverse B. So by calculating the matrix exponential Si minus A inverse, this comes out to be 1 over s plus 1 plus 1 over s 2, and it's so by putting the value of the Si minus 1 inverse in the this equation number 2 g of s, and plugging all the values of the C and B matrices, the values comes out to be s plus 2, s plus 2 into s plus 1. So here we are having one pole is cancelled with one 0, and the values comes out to be 1 over s plus 1. So by taking the inverse Laplace transformation, the g of t, the impulse response, is equal to minus t, which shows that when as time approaches the infinity, the natural response, the response of the impulse response of the systems goes to 0. So which is the we show that this system is BU stable. So thank you.